Okay, I believe we are starting, so you should be able to see us, both of us. Actually, I am Fabrice Tossi. I will be your chair for tonight. It's my great pleasure to introduce tonight Juan Camilo López Carreño. So who is Juan Camilo López Carreño? Dr. López Carreño, I should say. He's very famous for our Wolverhampton audience. People from the University of Wolverhampton. He's one of our favorite lecturers there. He's teaching quantum mechanics, solid state, a lot of different things. I believe some electromagnetism, he's doing some labs. Well, someone that we know very well is teaching a lot of different types of physics. At the international level, it's also famous for his research in quantum optics, in the quantum theory of light in particular. And this is what he's going to tell us about today. And regarding that, well, I should have said Dr. López Carreño for two reasons. First, because he's a recent doctor of science. He graduated last year, or 2019, end of 2019, I believe. And I've got his thesis there, and it's really remarkable because it opens with this saying, this motto, which is, I cannot pronounce it unfortunately because this is the old Shakespeare-like conjugation of English. It starts with "out of darkness comes light," which is the motto of Wolverhampton actually. And this thesis, which you can find online, is remarkable because it has this fantastic introduction. The first chapter of the thesis is making a really outstanding overview of light, not only on the scientific level, but it starts actually by quoting the Bible. I've got here some picture of Caravaggio, some paintings about Emmaus, a lot of different things. So it's extremely interesting, extremely modern. I invite you to try to find this thesis, if only for the opening chapter, which is really a piece of art, I would say, much more. It's almost some literature. It's extremely well written, informative. And for people who want to find the text itself, to read it, then maybe they'll have the chance to get a taste of this in the time that Camilo will tell us about the nature of light. What is light? If it's a wave, a particle? Well, nobody actually knows. I forgot myself, which was my personal option on that. And we'll see what Camilo will have to tell us about that. I'd like to mention as well that we are going to listen to someone who is extremely famous now, because for this work, for his research that he did, he actually was recognized the best physicist in theoretical physics of condensed matter in Spain, because he defended his thesis in Madrid, the Universidad Autónoma de Madrid. And at the national level, it was recognized for the year 2019 as the best theoretical work that was produced in condensed matter, in theoretical physics. So it's a great achievement. We are very pleased to have this outstanding, exceptional young researcher and great teacher to address us tonight, to tell us about what he thinks about light. So Juan Camilo, please, for the next hour or so, we are going to listen to your wisdom. Please.
Okay, thank you, Fabrice, for this very nice introduction, very nice and kind introduction. And so, as you said, today I'm going to speak about the so-called wave and particle duality, which is a phenomenon that was first observed, or is a controversy, or kind of a paradox that initially arose when scientists were discussing about the nature of light. So when they were asking, what is light made of? And so that's the topic that we are going to discuss today. We're going to go through the history of the developments that led some people think it was one way, or the reasoning that other people used to say no is completely the opposite, and then to see if there is something like a middle ground that we can all stand and make the choice. And at the end, I will say whether this thing that initially applies to light, if it applies to something else, to other types of physical particles or physical things that are in the universe. So as I said, let's start with considering light, which is the object that first led to this duality. And so if we are going to speak about light, and so we want to answer the question of what is light. If we go to the Encyclopedia Britannica, the first line of the definition of light is the electromagnetic radiation that can be seen by the human eye. So what can we learn from this definition? So it says that it's something, the electromagnetic radiation, but we will go to the details of that during the lecture. So it's something that is coming from the objects that we can see, and light is the thing that are coming to our eyes. So when we go walking and we end up with this beautiful landscape, so every single point that we see on this landscape is sort of reflecting light, so that the way we understand it now is reflecting light, and this light is coming from this point towards our eyes, and that's the mechanism that allows us to see. However, this was not the understanding of, or the scientific understanding on the process of seeing, or how we perceive light. Back in the antiquity, Ptolemy, he was one of the first ones to be busy with this problem of how we perceive the universe and how we can observe light. And actually, his theory is what is now called the extramission theory. And the theory was saying that actually, from our eyes, there are some sort of, for the lack of a better word, messengers that were coming out of our eyes. They were traveling through space, and they were sort of scanning the universe around us. So, for instance, the room we are now, and so they were getting in touch with the objects around us, and then they were coming back with the information, and that's how we perceive the universe. So now, for our minds, this sounds like completely nonsense. But actually, this theory comes from the observation that, and I'm sure you have seen this, if you have pets, or if you have seen pets or these house animals on the streets during the night, that some of them, when they see light, well, it looks like from their eyes, it looks like there is something that is emitting light outside, right? So you can see here this dog, or the felines, the cat. This you can see perfectly with cats. And so, well, but there are some drawbacks about this theory. So, for instance, if I have poor sight and I want to try to see something that, so if I'm struggling to see something, then I could simply ask someone else to watch the same thing. So now both our messengers are illuminating this thing that I'm trying to observe, and therefore my sight will improve simply because I have these extra messengers from someone else. Of course, this is not the case. It doesn't matter how many people are watching the same thing. If my sight is bad, I will not improve the sight. But also, this theory is not able to explain why. Well, it's a very fundamental observation that we can make every night, and this observation is that there is darkness. If there were some messengers or some light coming out of our eyes, then it wouldn't be possible for us to perceive darkness. Then the years passed, and it was not until the golden years of the Islamic science that Al-Hasan actually said, no, this theory cannot be correct. And actually what is happening is that our eyes are actually collecting the light that is coming from outside. So light is being reflected from the objects, and we are merely collecting the light, and the images are being formed while in our eyes. And that is the way in which we perceive the universe. And so he developed a whole treatise on this, saying that, well, there are some light sources, for instance, the sun, or more recently, light bulbs, that illuminate the objects. Then these objects are reflecting the light, and that is how we can perceive both the shape, the colors, and all these optical properties of the objects. That's how we perceive them. And so in his treatise, he says that each point of every color body illuminated by light, there is emission of light, so this issue of light and color along every line, every straight line that can be drawn from that point. So what he's trying to say, he's using a very different language that we currently use in our scientific books. But what he's trying to say here is that first, light is traveling in straight lines, and that every point that is on an object that we are observing is sending light, or is reflecting light that we are later collecting in our eyes. And that's the process in which we can see. So we reconstruct the object from all these light that are coming from the different points of the object that is being illuminated. And so by this time, and please look at the times. So we are almost in the year 1000. And so by this time, we know that light is traveling in straight lines, and this observation we can do by the ocean in these so-called light shafts. So here is perfectly clear that light indeed is traveling in straight lines. And it was also known something called the law of reflection. And this law of reflection, what it's telling us is that when light is being reflected from a surface, let's say a mirror, or in this case, the surface of the lake. So the reason why we can see a reflected image of this mountain on the surface of the lake is because well, light is being reflected from the surface, and this reflection is taking place in a very particular way. So there is one ray of light that is reflected from the top of the mountain, which is shine here. So let's say through this line. And then if we trace another ray that links our eye, or in this case, the camera that is taking this picture with this point through another ray like this, then the direction that is normal to the perpendicular, so that is normal to the surface, so that is perpendicular to the surface that is reflecting the light, the angle that the initial ray is making onto the normal is equal to the angle at which this ray is being reflected, right? And this is known as the law of reflection. So by this time, these phenomena they were observed, and so although they were observed and they were theorized about why these things were happening, the discussion about the nature of light was not an important topic. It was not something that people were interested at the time, right? It was only like to describe the phenomena instead of asking the question about the composition of light. But it was not until the coming of the Renaissance that we have the development of the scientific method, and of course we have to speak about Newton. And so Newton is more famously known because his development of mechanics. So in 1686 he published the Principia Mathematica, in which he developed mechanics, and to develop mechanics he also develops what we now call calculus. And this publication of the Principia Mathematica, as you will see, will be a central role, or it will have a very important influence on his theory of light. And so although he was working on the theory of light at the same time, you will see that the publication of his treatise of light was at a much later stage. And I will discuss on why there is such a delay in the publication of the two things in the following minutes. But so, the way Newton understood light was coming from a mechanical point of view. So he tried to understand light from mechanical arguments. And so he used, so in mechanics, we are used to describing objects that are, and if we remember Newton's first law, it says that, so that's the law of inertia. It says that if an object is moving in a straight line, it will continue moving in a straight line unless there is something that is acting on it. What else travels in straight lines? Light travels in straight lines. So he said, okay, we can understand the principle of reflection, the law of reflection, as a mechanical phenomenon. And so let's say that we have a particle. We throw the particle or this ball against the wall, and we will see that the angle at which this ball hits the wall is the same angle at which the ball leaves the wall, is bounces from the ball, right? So this example here is the same thing I mentioned in the previous slide with light, but now we are understanding it in terms of particles. So this analogy of objects moving in straight lines unless there is an external force acting on them led Newton to think about light in terms of these little balls. So he thought light was composed of very small corpuscles, so small particles, that were following mechanical laws. And so by the time there was this effect known as refraction, which is the bending of light when light goes from one medium, so let's say it's traveling through air here, then it hits a block of let's say glass, and then because it changes the medium in which light is propagating, so here it's on air and later on it enters glass, because of this change in the medium in which it is propagating, light will bend. And this is the reason why, if, for instance, we put a straw in our glass of water, or in this case, a pencil, it looks like the pencil or the straw is broken, right? But it's an optical effect because of the two different mediums. So in this case would be the air and the water. And so how did Newton understand refraction? Well, he said light is made of very small balls. And so the reason why the beam or this ray of light is bending is because the glass, if we keep on going with the image I was showing you before, it's because glass is acting, is making a force pulling the particles into the medium. So in this case, before moving, before entering the glass, the particles feel an attractive force that is pushing them or pulling them into the glass. Then they are traveling inside the glass, and after they leave the glass, they feel an opposite force that is pulling them, so that they don't separate from the glass. Right? So, and that's the reason why the beam of light is changing the direction. And so you see here, he's speaking about forces that are acting on these corpuscles. And so he's saying that that the glass in this case is pulling the particles, so pulling the particles towards it, and well, that's the way he understood refraction. Then he was making experiments regarding the light, and so well, the light he had available is what we now call white light, which is the light that is coming from, let's say, from the sun. And so he made an experiment in which, if you take a beam or a ray of this white light and you make it pass through a prism, which is something that you make of glass, then he could like unfold the light into its constituent colors. And so the effect here, I'm describing here is this. So you have a beam of white light, you make it go into a prism, and then because of the refraction inside this piece of glass, you have that the light is sort of separating in different colors. And so Newton decided, well, we need to explain this behavior. So before trying to explain, it is important to mention that at the time, well, the prisms that he was using were not probably were not as good as this one. So remember, we are in the Renaissance, so we are building these bits of glass, but it is not the manufacture is not ideal. And so the glass that he was using had some imperfections, and people thought that these imperfections were the responsible for the appearance of the color, and it was not something about the white light, but it was just like an artifact of the piece of glass. So Newton decided to make an experiment to check this. And so the experiment consisted in, well, he will take the light coming from the sun, he will collect a small beam of light, and he will make it pass through one of his prisms. Then he would observe the splitting of the different colors. And then he said, okay, if these colors that are coming from the prism that I'm observing out of the prism are an artifact of the prism, then if I filter, or if I collect only one of these colors and I make it pass through another by another of these prism, then I should see the unfolding happening again, because, well, these colors will be put there by the prism. And so he did the experiment, and surprise, he got the same color. So he filtered one of them, let's say violet, he make it pass to a second prism, and he collected the same color he was filtering before. So this is one of the first experimental demonstration that well, that these colors are indeed composition of white light, or that white light is made of the sum, or the sum of all these different colors, and are not an artifact of the optical setup. And so, speaking about this, Newton said that, or he could identify that white light was composed of 7 colors. And why 7 colors? This is interesting. Well, Newton was a very devout person. So he was a scholar of the Bible as well. And 7 is it's a holy number. Is the number associated with perfection. And well, how can it be that something that is coming from the heavens, so the light of the sun, is anything but perfect? So it has to be that the colors that are composing the white light are 7. So everything makes sense in his way of understanding the world. And the other thing that he could conclude from his experiments is that, so remember, light is for Newton, light is composed of little particles that have some mass and they feel some force, right? Now, he explained in Principia Mathematica, he explained that the relation between the force, so the force is proportional to the mass. So the larger your mass, the larger the force you feel, right? And so the reason why the different colors were separating when light was shining through this prism was because the particles of different colors have different masses. That's the way he understood light. So by the time he was working on his treatise on light, he was already a professor of mathematics in Cambridge. And on the other side, not long ago, there was the foundation of the Royal Society. And in the Royal Society, at the moment when Newton was working on optics, the person that was the expert in optics and light was someone called Robert Hooke. And so Robert Hooke was, well, he was doing the development of the microscope. He was the pioneer on microscopy, and he was studying a wide variety of biological samples, for instance, and putting them into the microscope. But by the time, so Newton and Hooke knew each other, they exchanged a lot of correspondence. The letters between them are, well, you can see them in libraries. And so they knew each other. And actually, Hooke was one of at some point when Newton was developing the mechanics and doing the development of the Principia, at some point he got stuck with the math. And well, he mentioned that to Hooke, and Hooke, well, supposedly in one of these letters, he gave Newton some hints of what he could do. So these hints end up becoming the foundation of calculus. But when Newton published the Principia, the way he acknowledged Hooke was saying that he was grateful to Hooke by rekindling his interest in moving objects. So completely disregarding the contribution of Hooke. And Hooke thought that well, that Newton was not being fair to him. And so there was this friction to start with. And so because Hooke was the expert of the Royal Society in optics and in light, when Newton sent his theory to the Royal Society, Hooke was the first one to read it. And when he read it, well, he was making some critiques, and some of the strongest critiques were the following. So Hooke says that white, so the white light, is nothing but a pulse or motion. And again, here he was not using the same language that we now use, but by pulse or motion, he means that that for him light is it's a wave. He was one of the believers that light was of a ondulatory character. So he said white light is nothing but a pulse or motion propagated through an homogeneous, uniform, and transparent medium, and the colors are nothing but the disturbance of this light. So he was opposed to Newton's theory or corpuscular theory of light. And moreover, he says, so he's speaking about the experiments that Newton was doing. He says that as to Newton's hypothesis of solving the phenomenon of colors, thereby, I confess I cannot see any undeniable argument to convince me of the certainty thereof. So it is known that Hooke, well, he was one of the best experimentalists of the time, especially in optics. and he was not convinced by the rigorosity of Newton's experiment. And it didn't help that Newton, he was very secretive, and he was not telling everyone how he did the experiment, or he was also saying, trust me, I got the very good prisms, but nobody actually seen them. So the experimental rigorosity was not the strong suit of Newton at the time. And so Hooke used this secrecy to critique Newton and his theory. And while Newton, it is known for not taking critiques in good spirits, and so he decided not to publish the results of his treatise. So he paused the publication of the results, and while he maintained this grudge for so long that he didn't publish the optics treatise, but after Hooke had died. So he waited Hooke to die to publish the results. So there is like this, you could say that Newton was keeping this grudge so deeply about the criticism of Hooke that he waited for him to die to finally publish his theory. Then later on, Newton became the head of the Royal Society, and the gossip says that that when he got to that position, he ordered to remove every single painting of Hooke, as to sort of erase it completely from the history of the Royal Society. Well, although we would like to think that that's the case, because that would certainly spice up the personality of Newton, while there is no actual evidence supporting that. What is a fact is that there are not many paintings from Hooke. Actually, this one that I'm showing you here, it's a contemporary painting from a contemporary artist. So this is not dating from back then. But whether it was Newton who decided or who ordered to remove all these paintings of Hooke from the Royal Society, well, we don't know. We know that there was this animosity and that Hooke was very critical of Newton's theory, but we cannot know about this decision on the inner workings of the Royal Society. But so let's move on from this gossip of the Renaissance and Newton, and let's go back to the theory of light. So while Newton was working on his theory, on his corpuscular theory, there were some other people, besides from Hooke and other scientists, who were working on a different theory that was based on light being made of waves. And well, the scientist that advanced most this theory was a Dutchman, Huygens, who used an ondulatory theory to explain the phenomena that were known at the time. And so for the phenomena of the refraction, he explained it in the following way. So instead of being composed of little particles, let's say that light is made of waves, right? And so we have this wave that is reaching the glass, the same glass we had before. And so he said, in the material, the speed at which light is propagating is slower. It's slower than it is on the outside when it's traveling through air. And so let's imagine that we are on top of one of these waves, and we are propagating towards the glass. When the right-hand side of the wave starts to fill the glass, so this point, when this bead starts to fill the glass, it will start to travel slowly. And because it will start to travel slowly, the front or this horizontal bar that is moving forward will not continue to be moving like this, but rather it will start to move like in a diagonal. And it will be moving in a diagonal because the speed at which the right-hand side is moving is lower than the velocity at which the right-hand side is moving. And so as a consequence, we will have that this motion will become bended. And so using this argument of light traveling slowly in the glass, he could explain the bending of the light. And so you see here, we don't need the forces that are acting on the light. And well, this theory of Huygens, he was predicting something very different from Newton. So from Newton, which was saying that light was made of corpuscles, and that corpuscles were feeling this force pulling them towards the glass, the speed of light inside the glass would be larger than the speed of light on the air. Whereas for Huygens, for this observation to work, light would need to travel slowlier in the glass than in air. And so modern experiments have demonstrated again and again that actually light travels slowlier in glass than it does on air. So Huygens has the correct explanation for the phenomena of refraction. And so for this experiment, so if we are based only on this experiment, we should say that light indeed is composed of waves. Other phenomena that were known at the time, and Huygens was contemporary of Newton, is the effect of so-called diffraction, which is what happens when a light source is illuminating a barrier or something that casts a shadow. So for instance, we have this image of some scissors. And then the reason why we see these sort of ripples or interference fringes around the shade of the scissors is because, well, light, when it reaches the edge of the object that is casting the shadow, so the edge of the scissor in this case, well, there is a bit of light that not only goes in a straight line, so straight ahead, but also it will also bend. So schematically, what is happening is that the light is not only traveling in a straight line like this, but a bit of the wave is also able to pass the barrier and illuminate areas that were in principle covered by the barrier. On the other side, if light was composed of corpuscles, well, the shadows would be completely flat or completely sharp. So we would not observe this diffraction pattern on these objects. So this was another evidence or another suggestion that indeed, or at least for these experiments, we can only understand light as being made of waves. Now, although Huygens was contemporary of Newton, you have to remember that Newton had already published the Principia Mathematica. He had already established this mechanics as a field, and so he was an eminence on physics, on science. And so by the time it was believed that how can it be that Newton, who has this brilliant mind and he has set the foundation for mechanics, how can he be wrong? So certainly there must be something. So the theory of Huygens was ignored by the scientific circles, right? But it was not until a couple of decades that another British scientist, Thomas Young, he presented the finding of one of his experiments, and this experiment would be later known as the double slit experiment, and it consists that we have a source of light and we make it pass through a screen, so a flat screen, in which we make a pair of slits, so narrow slits, so that light can pass through these slits, right? And so the experiment is as following. We have the source of light, we make it pass through this screen which has these two slits on them, and then at a later stage we measure and we see the pattern that arises because light is passing through this pair of slits. And so he did this experiment, and what he observed was a pattern like this. So here the red regions are the regions where light is accumulated. So red. So the red regions here are bright regions, so where there would be light, and the black regions are places where there is no light coming. So we have this pattern of bright stripes and dark stripes. Another point with this experiment is that if we use the theory of Newton for light, and we assume that particles, that light is made of particles, so the source of light is emitting particles, the pattern that we would observe when they pass through this screen where we have put these two slits will be more or less homogeneous. We wouldn't see the fringes that Young observed. But instead, if what is emitted here, instead of being particles, it's a wave, then when this wave passes through the two slits, we will have a phenomenon of interference, and this interference will yield the pattern that Young observed. And so this is one of the foundational experiments that proves the ondulatory nature of light, right? So the observation of Young is one of the one of the biggest experiments that demonstrate the ondulatory nature of light. And this was happening in England under the influence of the Royal Society. On the other side of the channel, we had the French Académie des Sciences, and they were also discussing about the nature of light. And so by the time Newton's theory was the canon, was the commonly accepted theory, but they were worried about the fact that they couldn't explain the diffraction. And so Huygens had presented a theory, but the French Academy was not convinced, and so they made a contest, so that to have the French scientists develop their theories as to and to explain the diffraction observation. And the person who won this contest is Fresnel. He was actually, he was not a physicist by education. He was an engineer, and maybe because of this education outside of the mainstream of physics at the time, he was able to dissociate or to separate himself from the corpuscular theory. He tackled the problem from scratch, and he came out with an explanation that involves waves. So he presented his theory to the academy, and actually, when he presented the result, one person of the tribunal of the academy, Poisson, he studied the theory, and he found a very particular effect that Fresnel theory was predicting about diffraction. And this observation would be that if we shine light into an object that casts a circular shadow, so never mind the actual object, but if we have something that that when we shine casts a circular shadow, then Fresnel diffraction theory suggests or predicts that there is going to be a bright spot of light right in the center of the shadow. And then by the time it was thought, come on, how can it be that we shine light into an object, we have this huge shadow, this huge circular shadow, and right in the center, where there is supposed to be nothing but darkness, we see the appearance of a bright spot. Well, it was a good thing that Poisson's word was not taken for granted, and they didn't simply disregard the theory, but they actually made the experiment, to the great surprise of Poisson that the bright spot was there. So they observed the diffraction pattern, but they also observed the bright spot right in the center of the shadow. And so this bright spot in this configuration now is called referred to as the Poisson spot. And well, this was one of the proofs of the correctness of Fresnel theory. And by this time, well, it's impossible to ignore the amount of evidence that points out that light is made of waves. And moreover, by the end of the century, the Scottish scientist James Clerk Maxwell, who was working on electrodynamics, he found that there were some that the way in which magnetic and electric fields propagate in space is through some waves, So doing something like this. So in blue, let's say we have the magnetic field. The electric field is perpendicular. So the magnetic field and the electric field are perpendicular. And the direction in which they propagate is perpendicular to the two of them. So if the magnetic field is oscillating in this direction, and if the electric field is propagating in this direction, is oscillating in this direction, sorry, the wave, the electromagnetic wave, would be propagating along this direction pointed by the arrow. And so in his derivation, and remember, he was not discussing light per se, but in his derivation, he found these waves that were propagating the electromagnetic field. And he saw that the speed at which these waves were propagating, coincidentally, were the same speed at which light propagates in space. And so, well, this was coming from other experiments that were trying to measure the speed of light. And so he found that, well, that these electromagnetic waves are moving at the same speed of light. So it's a good hypothesis to say that light is made of these electromagnetic waves. And so there is an important relation between the speed of light here, what we call c, and the wavelength. So the wavelength is the distance between two consecutive maximum of these waves. So for instance, the distance between this point and this point, or between two nodes of the wave. So for instance, the distance between this point and this point. And this is what we call the wavelength by this Greek letter lambda. And so the speed of light is the product of the wavelength and the frequency that we call f. And the frequency it's a number that dictates how often we complete one of these, one full oscillation. So we go up and down and coming back to the initial position. So how often we complete one of these cycles as a function of time. And so apparently, with all this evidence, it looks like light is made of waves. So apparently, we have settled the problem, and light is made of waves. And so we started the century with this way of thinking, and well, focusing on a completely different problem, we find the work of two British gentlemen, Rayleigh and Jeans, who were studying the so-called black body radiation. And the black body radiation is the electromagnetic emission that any object that has a finite temperature emits simply because it has this finite temperature. So what are we speaking about? So let's say that we have this little mouse, and we use an infrared camera. We will see that now the mouse looks like the figure on the right side of the picture. And now the different colors are associated to different temperatures, right? So we see here, for instance, that the temperature of the ear of the mouse is different from the temperature of the supposedly the belly of the mouse. And so these different colors are associated to different temperatures. And it says that, well, if the mouse is at, I don't know what's the temperature, the body temperature of a mouse, let's say 27 degrees, or no, maybe 37, more like 37 degrees, then well, there is a distribution of the energy that is emitted by the mouse as a function of this temperature, and the intensity of the light or this radiation that is emitted is different depending on the wavelength. Right? So, for instance, in this figure, we see that the cyan color is predominant or is more abundant than, let's say, the red one. Yeah? So we see that the density of cyan is larger than in red. So what Rayleigh and Jeans were trying to do was to quantify the intensity of light, so how much light was, or how much of this radiation was being emitted at given temperatures for different wavelengths. And so they were making these experiments with different objects at different temperatures, and if they were plotting the results. So in the x-axis, I'm showing you the wavelength. So remember, the distance between two consecutive maximum of the wave, and in the y-axis is the spectral radiance. So the intensity at which the intensity of the emitted light. So we see that at very short wavelengths, there is very little emission, regardless of the temperature. And then as we increase the wavelength, we see an increase of the intensity, right? So we see this sort of behavior, and then at long wavelengths we see it coming back to zero. And supposedly for very long wavelengths, the spectral radiance should be decreasing back to zero. And so they were measuring this, and when they tried to compare this with the classical theory of electrodynamics, the one that was developed by Maxwell, they found that, for instance, the observation was this one. So the line that is here in red is what the classical theory predicts at the same temperature of the blue line. So we see that not only it doesn't agree very well in the region of long wavelengths, but most importantly, this curve keeps on increasing. There is never a point at which the black curve comes back to zero at very short wavelengths. And of course, this is not possible, because it would imply that as the wavelengths become shorter and shorter, the amount of energy, so the intensity of the radiated light, would be infinite. And of course, that cannot be the case. And so, tackling this problem, and here we are developing the theories of thermodynamics, there was a German scientist, Max Planck, who said, okay, let's use the theory of thermodynamics, but now let's assume that the energy of this radiation emitted by the black bodies, by these objects that are at finite temperature, it can only be given by so-called small packages of energy. He referred to them as quanta, and so he said, if the energy associated to this radiation is given by some constant that coincidentally is called the Planck constant, because he introduced it, multiplied by the frequency of the wave, then he could reproduce exactly the observation of Rayleigh engines. So I'm not going to plot on top the result obtained by Planck, because it would lie exactly on top of for instance, the blue, green, and red lines for different temperatures. So to explain this black body radiation, Planck introduces this concept of the packages of energy that light can have. Okay? And so by introducing this concept of quanta of light, of packages of light, we are sort of coming back to saying that light is composed of particles. Not particles as Newton thought about them, it's not small balls, right? But it's a collection of packages of energy. So it's like, although we have all this evidence about the undulatory nature of light, we are coming back, and this is this is the foundation of the 20th century. So we are coming back to an explanation involving a corpuscular theory. About this, Einstein, at the same time, he was working on a problem that couldn't be explained at the moment, and it was actually a problem that, for which he obtained the Nobel Prize. So he didn't get the Nobel Prize for the theory of relativity, but he obtained it for the explanation of the so-called photoelectric effect. And this effect is the following. Let's say that we have a material that I'm represented here by this gray region, and let's say that we have a collection of electrons that are represented here by the blue balls, by these blue dots. And so the observation, the experimental observation of this effect is that when experimentalists were shining some light into this material, they observed that there was a threshold frequency, and this is important, there was a threshold frequency above which they observed the emission of electrons. So if the frequency of the beam of light that was shining onto this object was above a certain threshold, they observed a current, the appearance of a current coming from electrons that were being detached from the material. Below this threshold frequency, they wouldn't observe any current. Right? So if we are below the threshold frequency, there is not any current. regardless of the intensity of the field, of this beam. So we can use a very, very intense field, but if the frequency of the wave, of the light, is not above the threshold, we don't see anything. However, if we are above the threshold, it doesn't matter how small the intensity, we will observe an electrical current. And then what Einstein said is that, okay, I'm going to use Planck's hypothesis of the photons being, or the light being composed of these packages of energy. And if that's the case, then we can imagine that light is made of small particles that carry this energy that was written by Planck. And then he can explain this effect by a simple collision. Let's say that we have one of these particles of light that has a given energy. Then it collides with one of the electrons in the surface, in the material. And then, because of this collision, let's say that it's an elastic collision, then it gives the energy. So the photon gives the energy to the electron, which now uses this electron to be ejected from the surface and to have a kinetic energy. So, using the hypothesis of Planck, Einstein is able to explain the photoelectric effect using a mechanical explanation based on Newton's theory. And well, although at the time Einstein was not using the word photons, as I just did, because I'm just so used to using the word, he was always speaking about energy packages or quanta of light, but photons were later on popularized by the usage of people. And so by the time of Einstein, we are back to the point that light is composed of photons, right? And these photons we can imagine as units of energy, as small balls, if you want. Well, I don't think a ball is a good representation for a photon, but we can imagine that light is composed of these units of energy that are traveling through space. And so, while Einstein could not ignore all the evidence for the undulatory nature of the waves, and he said, and he was the first one to introduce the so-called wave-particle duality. And so he says that it seems that as though we must use sometimes one theory and sometimes the other. So for one cases, we must use the undulatory wave, so for instance, to explain diffraction, and use the other another times, for instance, to explain the photoelectric effect. And there are cases in which we can use either one. And so we are faced with a new kind of difficulty. We have two contradictory pictures of reality, so one being particles and the other being waves, that separate and separately, neither of them fully explains the phenomena of light, but together they do. So it's impossible to detach one from the other. We need to have their representation as waves, but also we need to have the representations as particles. And so, this being said, now the question is whether, so now that we know that there is this duality of light, we would like to know if there is something special about light, or if there are other things that also display these phenomena. And so we're going to use another of the results of Einstein, and this is coming from the theory of special relativity. And in this theory, he introduces an important equation that relates the energy of a particle in terms of the kinetic energy and the energy because the particle is moving, and the so-called rest energy, the energy that the particle has or that the object has simply because it has some mass. So this term would be the rest energy, and the first one would be the kinetic energy. So although this equation may not look familiar to some of you, if we consider objects that are not in motion, so if we neglect the kinetic part of the equation, we recover, well, one of the most famous equations that I'm sure you have seen before. So the energy is equal to mc squared, c being the speed of light. But photons are not massive particles. They don't have a mass associated. So all the energy of the photon is concentrated in this kinetic energy. And here, P is the momentum that is associated to the photon. In classical physics or non-relativistic physics, this momentum is given by the mass of the object times the velocity at which the object is moving. But in general, we can express the momentum as P. And so the prediction of this energy by the theory of Einstein is that the energy is equal to the momentum times the speed of light. But on the other side, from the hypothesis of Planck, we have a relation between the energy and the frequency of the wave. Right? And that means that we can we can solve these two equations for the momentum and express it in terms of the frequency of the wave, of a wave, and the speed of light. Then using the relation of Maxwell that I introduced some slide before, so that the speed of light is equal to the wavelength times the frequency of the light, we can express the momentum in terms of a wavelength. And so doing following these steps, in 1914, a French scientist, Louis de Broglie, he wrote in his doctoral thesis he hypothesized that maybe we can associate this wavelength to objects that are massive. Yeah? Because we can solve for the wavelength here, so it would be the Planck's constant divided by the momentum. But then, the momentum for massive objects is given by the mass times the velocity at which they are moving. So now the question is whether massive objects can behave as well as waves. And so let's consider the case of an electron. And so if we know the mass of the electron, so it's 9 times 10 to the minus 31 kilograms, so it's relatively a light particle. And let's imagine that this electron is moving at 0.01% of the speed of light. So a velocity that is very, very, very slow. Certainly is not a relativistic velocity. And putting these two numbers into the Broglie equation, we have that the wavelength associated to these electrons is about 20 nanometers, which is 20 times 10 to the minus 9 meters. So it's very small, but it's a wavelength that is within the reach of experimental observation. And so we can make such an experiment. For this, so when I say that is within the experimental observation, it's because we want to make an experiment like Thomas Young did, so a double slit experiment. And to observe this interference pattern, we need the separation of the two slits to be of the order of magnitude of the wavelength. So more or less about the same size, more or less 20 nanometers around this. And so we have a beam of electrons, we shine it through one of these double slit screens, and then we observe the pattern that is generated. We can perform such an experiment. And so what I'm showing you here in this black screen is the arrival of an electron to a screen. And so every time you see a white dot appearing on the screen is one of the photons that came from whatever is emitting this electron, like an electron gun if you want. And then passing through the double slit and reaching the final screen where they are observed. And so, we can make this experiment many times with many electrons. And I'm not sure if you can see the pattern that is arising. So you see that the white dots are concentrated in these regions, in these 5 regions. And more importantly, we have we can see clearly regions where these white dots are getting most away from. Yeah? We see this region here, this region there, and there, where relatively few of these electrons are getting. And so I think at this point you can already identify that the pattern that is observed with electrons matches completely the pattern of that Young observed with light. So what this experiment is demonstrated is that electrons, which are particles that in principle we think of as particles, when we think of an electrical current that is whereby electrons are moving from one place to another, we don't think about them as waves. We think about them as little point charges that are moving from one place to the other. But this experiment is demonstrated that electrons, which have mass, they also behave as waves. And so with this observation, well, if massive particles behave as waves, there must be an equation that describes this motion, right? Because this is certainly not following Newton's equation, because it's being represented as a wave. And so, who obtained this representation of quantum objects? And now here we introduce quantum objects to generalize electrons. Was Erwin Schrodinger, so another German scientist, and he introduced his famous equation. So this is an equation, a wave equation, so to represent this undulatory nature of the particles, which is a differential equation. So this is the variation of an object called the wave function as a function of time. And the way, so what dictates this variation in time is a function, or is an object called the Hamiltonian, which is associated to the energy of the particle that we are describing. And so from the wave function, we can recover a so-called probability density, which means that if we have this probability density and we plot it in space, for instance, we can say, for instance, what is the probability to find the quantum particle in the region from, let's say, from this point to this point, simply by summing the area below this bit of the graph. And so there are some striking observations about this theory or this equation. And the first one is that we cannot know precisely the position of this quantum object simply by knowing the wave function. We can know the probability to find the particle in this region by summing this area, but we don't know where the particle is. That is until we make a measurement. When we make a measurement, we say, oh, the particle is here. But before we do the measurement, we can only know the probability of finding the particle at some point in space. And because of this observation, well, Einstein was shocked by this result, and that's why he made this comment that God doesn't play dice with the universe. So how can it be that we have a theory that doesn't allow us to precisely predict where the particle will be, and instead we have to leave things to chance? So Einstein was very opposed to this quantum theory. And well, Schrodinger, although he developed this theory, he was also not very happy about the consequences that this equation was predicting. And in particular, what was the most striking to Schrodinger is that, well, because of the nature of his equation, because it is what we call a linear equation, that means that if we know two solutions to Schrodinger equation, two independent solutions to Schrodinger equation, let's say the wave function 1 and the wave function 2, so knowing these two solutions, we can build another solution as the superposition or as the sum of these two wave functions. And this sum or this superposition is also a solution to the wave function, to Schrodinger equation. And this fact that the superposition is also a solution, it can give rise to, for instance, a particle being given the possibility or the probability of being at two very distant places at the same time. Right? So remember, we're speaking about probabilities. We're not saying that the particle is at the same time at two different places. We're saying it's probable to find it at these two distant places. When we measure, we will find it at one place or the other, never at the two. But we will have so before we make the measurement, we cannot say whether it is at one place or the other. We can only say that it's that can be on both. It's a superposition of the two places. And so to illustrate how absurd this theory was, Schrodinger came out with a thought experiment, which is the Schrodinger's cat experiment. And he said, imagine, let's say that we have a box, and in that box we put a radioactive particle, which when it decays, and this radioactive decay happens at random, so we don't know exactly at which moment in time this particle will decay, but when it does, it will release a hammer that is going to break a vial of poison. And if we put inside the box as well a little cat, Well, once the poison has been released, the cat would die of the poison. But if the radioactive particle is not decayed, the hammer is not released, the poison is spilled, and the cat is happily alive. And so let's cover the box and let's try to describe the quantum state of the cat. So because we don't know what is going on inside, because we don't know at which point in time this radioactive particle will decay, well, we cannot know whether the cat is dead or alive at any given point, right? It is only until we open the box to check whether the cat what's the situation with the cat, we can only say that the cat is in a superposition, in a quantum superposition of being alive and being dead. And so Schrodinger thought that this thought experiment was revealing how absurd this theory was, but it was quite the opposite. And it has been realized experiments in which we have this superposition even with microscopic objects. No, so not with cats, but with microscopic objects larger than electrons, or molecules and things like that. No, not full feline. And so if we have, so with this possibility of having the superposition and being or having this formalism to describe the wave function of a quantum object, we can repeat the two-slit experiment with one of these objects, right? And so instead of being a particle or a wave, what we are propagating in space is the wave function. And so with some probability, the particle will, or the object will pass through one of these slides. With another probability, will pass through the other slit. And then what's happening between the slits and the screen at which we are observing the pattern is that we have an interference of the probabilities. And this interference of the probabilities is what gives us this interference pattern that agrees with the observation of Young. Right? But now we are not speaking about light, we are speaking about quantum objects, yeah? An electron or any other quantum object, a neutron, a proton, anything. And so, if instead of letting this wave function propagate freely in space, if we introduce an observer, and so this observer, what it's doing is opening the box, saying whether the cat is dead or alive. So in this case, for the slits, it's checking whether the object passed through one of the slits or the other. So if we have this observer that can verify through which slit the quantum object has passed, and we repeat the experiment many times, what we see in the screen at the end is that while the interference pattern has vanished. And so with this theory, what this is saying is that, okay, we can describe object, we can describe nature, and we cannot associate a particle nature or a wave nature. We can only say that there is some probability, and it depends on whether we observe the phenomena and at which point we observe the phenomena. So if we observe before it passes the slit or after it has passed the slit. And so what this theory is saying is that, well, in principle, we could have this interference pattern with anything, because quantum physics is a theory that applies to everything. So now an interesting question would be, how about we make a double slit experiment with us? How would we be able to behave as waves as well? No? Because I think most of us would identify it as being closer to a particle than closer to a wave. So let's consider what happens with us. So if we remember the Broglie equation for the wavelength in terms of the mass and the velocity, and we assume that we are someone with the average weight of someone in Britain, which is somewhere between 70 and 80 kilograms, and remember, we need to be able to pass through the slit. So let's aim for a wavelength about 2 meters. That means that the velocity that we need to perform this experiment would be 4 × 10⁻36 meters per second. And to give you an idea of how diminutive this velocity would be, or how this velocity is, in the entire age of the universe, which is a very huge number, traveling at this speed, we wouldn't even cover half a meter. And so, of course, making an experiment at this velocity with us is, well, it's not feasible. We could not perform such an experiment. And on top of that, well, we are covered by, well, we are surrounded by an environment, right? We are in contact with molecules of air, with light, with our neighbors, and so on. And so all these things would make an observation that would collapse our wave function, and then we could only pass through one slit or the other. So because of this observation, we wouldn't display an interference pattern like electrons do, for instance. But although we being well, as massive, so as compared to an electron, we are a supermassive object. But there are objects that are heavier than electrons that do display this wave-particle duality, among which there are neutrons, protons, and I think one of the largest molecules that have been observed displaying this wave-particle duality is the so-called Fullerene, or C60. So it's a ball made of 60 carbon atoms. And with these molecules, it has been observed this wave-particle duality. So to finish the presentation, and so to give back an idea of what we are discussing about, so we have this object that, depending on from where we are looking at, we see one thing or we see the other. So, but it's not only that we could say that something is waves or is particles. Rather, we have to describe the wave function, and with the wave function, we have all the knowledge about the behavior of this object. And so they can behave sometimes as waves, sometimes as particles, depending on when we do the observation and the experiment that we produce. But the fundamental object that we should describe is a wave function. And so here I reached the end of my presentation. So if there are questions, I'll be very happy to answer them.
Thank you very much, Camilo. It was really interesting. It reminds me your last calculation of this book of Vonnegut, the Siren of Titan. I don't know where to put the E or the I, but there is a character with a wave there. Do you know this book?
No, unfortunately no.
Because it will certainly inspire you. So now comes the best part of the talk, which is the one where you can ask questions. So there is a little box somewhere where you should be able to type your questions. Unfortunately, I will have to read them, which removes a lot of the patient of things. But please do ask questions, because that's really what makes these talks interesting. We have a chance to challenge or manifest ourselves what we think. So we've got a first question by Douglas Blundell, who asks, your account of Hooke and Newton suggests that the greater the genius, the greater the controversy. Do you think we are past that phenomenon in physics these days?
Well, I think one of the reasons why Newton was able to ignore all the evidence, it was because of his importance, and because the scientific method and the answer to what constitutes a scientific proof, a demonstration of something, were not so developed at the moment. Now, I would like to believe that this has changed now, and it's just not because someone is saying that, someone important has saying that it has to be true. So, for instance, one of the examples that come to mind is for instance, Josephson, who, well, he had this brilliant idea when he was a PhD student to explain superconductivity. He got the Nobel Prize for that. And then, well, once you get the Nobel Prize when you are doing the PhD, you feel invincible, no? And so you start to throw theories to every day, and of course some of them are so twisted and so unscientific that people are saying, "But come on, this cannot be true." And even though he is someone with a Nobel Prize, well, the scientific rigor is above that. You know? So I would like to think that. That we are past that point. That it doesn't matter how brilliant you are. If it's not agreeing with the measurements, well, I'm sorry, but it's incorrect.
Well, Newton was notoriously a nasty person. I don't think it goes with genius, because Einstein, on the opposite, was kind of good, benevolent person. So after this this social question, Douglas has another technical question. He asks, how big is a photon? Is it as big as an electron? Is a microwave photon much larger than a photon of visible light? It's like a question for an exam student.
Well, this is actually a very good question. I don't think anyone has the answer to what's the size of a photon, or for that matter, what's the size of an electron. We all, so if when I speak about an electron, well, you imagine a point charge, no? So it's something that doesn't have a finite width. So, well, I guess we can, as we perfect our measurements, there can be a point where we actually make one of these slits where the electrons cannot go through because they will be larger than this slit. I don't know if we will ever reach that point. Now, whether one electron that is of one frequency, let's say microwave, is larger than one red photon, if you want, well, this I don't know. Well, they have a different energy. This much we can say, but about the physical size or like the volume that they have, I don't think we have the answer. And remember, we need to speak about the wave function. We don't speak about the size of the particle anymore. We speak about the wave function. And so we have to speak about the size of the wave function, and then we can compress the wave function as much as we want, regardless of the frequency of the oscillation. I'm not sure if we can make a statement about the size of the photon and relate them to the frequency that they have, the energy that they have.
Yes, and like all questions regarding the nature of light, is very difficult to make a definite answer. According to the standard model, it's a point-like particle, so it has no extension, but it depends on what we interpret as light. We've got lots of questions, which is really good. Please ask questions, but then Camilo, maybe try to be brief so that we can read all of them. So we've got a question from David Kola, who says, amazing talk. Is there any deep mysteries left about the nature of light?
Well, there have been people that are describing particles of light, or that involve light, that behave as if they have a negative mass, and maybe the David Kola is familiar with this type of objects, yeah, that are particles that are made of light, but not only light, they have something else, a material part, that actually when you kick them in one direction, instead of moving along that same direction, it's going in the opposite direction. So you kick them towards the screen and the particle is moving away from the screen.
Very good. So that's what is mysterious about light, is what David is doing with them. Then we've got questions from Naina Reddy. She asks, is light a quantum object as well?
Yes. So everything can be thought of as a quantum object.
Then from Sana Khalid, she asks, how different would you predict the development of theories around light if Newton passed away before Hooke? Very good questions. Dystopia, maybe.
Well, remember that around the same time, there was Huygens who was developing the undulatory theory, and Huygens was also ignored by the French Academy. So I don't know how big an effect was the controversy between Hooke and Newton for the French to ignore other people.
Then we've got questions from Amir Ramani. He says, hi, thanks for the talk. I've got two questions, although I can only find one. So, but first question is, which of the particle or wave nature of light has the central role in modern theory? It seems to me that the statistical features are important only when we consider the particle nature. Is it the case? Very technical question.
I believe so. I think, well, the modern theory of quantum optics is based around the corpuscular nature of light, the correlations between photons, right? So I would say that this is playing a more central role than the undulatory optics.
Then a question from one of our students, actually, Katarzyna Sopinska, and she asks, which is a bit surprising, she should know, because I believe she should have studied that in optics, actually. She asked, could you explain a little more about how this dot appears in the circular shadow, so the Poisson dot? It's difficult for me to imagine.
Well, you have the light that is being shown into this object that has a circular shadow. So light is reaching the edges of the object, and then we can think of the front of the wave, so the first part of the wave that is reaching the object as an infinite consecutive points that each of them are emitting waves, right? And so we make the interference of all these little waves, and we project them into the screen. And while this interference, this gives back this little point that appears inside within the shadow.
So we've got follow-up question from Naina already to what you answered. She was asking if light was quantum. She asks now, so would you say light is a wave or a particle or a quantum object? Thanks again.
Well, by saying that it's a quantum object, I'm saying that it can be both, right? So a photon on its own is like the particular or corpuscular interpretation of light. So a photon would be so light is composed. It can be represented as a quantum object, and so sometimes it behaves as particles, and so we speak about photons, and sometimes it behaves as a wave, right? But it's the same object, it's the same quantum object. And photons are just one representation, the corpuscular one.
Then we've got a question from Adam Skyfe. He asked, is there a leading alternative to God playing dice?
Well, if you read Stephen Hawking, well, he doesn't need God to spin the universe. No? So this is a philosophical question. No? Well, Einstein was very religious, so of course he included God. But I think more than speaking about what God does in his free time, I think what he meant was that physics, being an exact science, how can it be that an exact science was not able to predict something precisely, and we have to leave something to chances? And I think that's more the background of Einstein's remark.
Okay, then we got John Kane, who asks, has the double slit experiment been carried out with effectively one photon or electron at a time? If so, aren't they effectively at both slits at the same time?
Yes. So actually, this experiment that I was showing you, with the white dots appearing on the screen, was done with individual electrons passing one by one. So it's not an effect of many electrons interfering with themselves. Is the wave function of the electron that is interfering, so it's passing effectively through both slits and then providing the interference. But the one electron at the time.
Yeah, well, I'd say it depends on the interpretation. If it's a wave interpretation, multiverse interpretation, various possible answers. That's what makes the questions fun to ask, because you can ask anything and all the answers are correct. Another question from one of our students, Ravi Singh. He asked, I wanted to ask if any aspects of your research were undermined or assisted by the wave-particle duality. Very personal question.
Well, we are quantum opticians, so that means that we like to think about light as photons. So for our research, I would say no, we don't use the fact that light has this duality. We focus on the quantum part, or in the particular part of light. So the quantum, and we investigate the ways in which photons are correlated with each other.
Katarzyna asks again, how can a photon have a size if it has no mass?
A size?
How can the photon have a size if it has no mass? If you're massless, to some extent, I guess is the question.
Well, it depends. So what has a size or what has a physical extension is not the photon per se. Is the wave function. The wave function is the one that is expanding in space. So if you ask me, well, this photon it's a point, right? It's the probability that is spreading in space, not the photon. It's not like we have a stretched out photon. traveling there, no? Like
all the answers are correct, but of course they should not contradict each other. A long question from Sana again, so I'll read it completely. If the speed of light is so large and the size of it, of the photon, is small, could these wave-like properties simply be just a result of a combination of its speed and our limitation in observation, including the relation of our times move in our frame, if that makes sense, in parentheses. So everything, if observed in its simplest form, is just a particle.
I don't understand the first part. So if
so it's linked to the speed of light. The speed of light is large. The size of the photon is small. So could the wave-like property be a result of the combination of the speed and our limit in our resolution in the observation?
Ah, so it's like we see a difframinated photon, something like that.
Yeah, I would say the answer there is that it's the effect you described are not involve particularly the speed of light, right? The electron could be very small. You said yourself we should move at this terribly small speed to see the thing happen with ourselves. So it doesn't involve the speed of light. There is a lot of interesting thing that happens with relativity as well with light. Yeah, the proper time is 0, so the lifetime of a photon is 0. A photon dies at the same time it's born. Lots of different things in relativity, but not there. Let's move on because lots of questions. Then we've got Ravi again. I wanted to ask if it's the same question. So Ravi asked twice. Robin Hewitt now is asking, can an experiment similar to the diffraction of light around an object to create the central dot of light be done using electrons? Good question. So it should be, because the electron is also.
Yes.
I don't know if it's been done. It's certainly it might have been done. De Broglie himself proposed the diffraction of electrons in the crystal to prove the wave nature of the electron. He might have proposed the Poisson dot, because Poisson dot was what convinced everybody. Yeah? The influence of Newton was so large that nobody thought that it was a wave, despite the diffraction and everything. And Poisson, it ridiculed the theory, said, look, it would lead to this absurd thing. It was one of the first time when the experiment convinced people. Mm-hmm. Sana asked again, would there be anything present to contradict this theory? So she was carrying on the previous question. So maybe we'll skip this one because we already forgot the previous question. Kasha asks, is the observer basically any kind of interaction with the object? Is the observer basically any kind of interaction? So yes, answer. Mm-hmm. That question was a follow-up to what Camilo was saying previously. Thank you. David Kola again. How can an electron have a mass and no spatial extension? This is related to the previous question, I believe.
Yeah, so because then it would be infinitely dense, you know? And then that would be like a miniature black hole. You know? So certainly it must have an extent, but at the moment we can only say that it has less than a given size. I don't have this size on the top of my head, but it's a very, very small size. We can only say that it doesn't have a radius that has a radius smaller than a number. We don't know the size yet. So it must have an extension, and we're not even sure about that, no? Because, well, we haven't measured it. No? But there is a.
And the last question. And the last question we've got in our list, so it still leaves a bit of time for the people hungry for more to ask. So short answer, it's a complicated question. It's Adam Scaife again who asks, to rephrase, he says, is there a leading alternative to us having to accept the probabilistic interpretation?
So okay, so maybe what it can be done is that the objects, so it's not that the wave function collapsed at some point, is that actually there is like a unfolding of universes where the particle is at different points in space according to this probability. So at any, let's call it at different universes, the particle is at different positions. Okay? And then, while the probability is vanished from this interpretation, it's just that we are in one of these many universes that in which the experiment could be carried out.
Yes, I would say that I agree that's the leading alternative. So Adam, if you are like Einstein distressed by the probabilistic interpretation of quantum mechanics, there is someone, John Bell, who was on the advice of the opinion of Einstein that it should be deterministic. But he demonstrated that to be deterministic, then the world has to be non-local, which means that things like action at a distance, or not, if not action, at least correlation or connection at a distance should exist. And this is very much opposed to the dearest aspect of Einstein, which is more than determinism, is locality. Yeah, the fact that things behave locally. It's the big masterpiece of Einstein. So actually, Einstein was dead by the time, and they say all the better, because he would have liked this even less, that the world maybe is deterministic, but it's non-local. That would have been even worse for Einstein. This being said, we have no more questions. So Camilo, unless you have more observation comments you wish to make.
That's fine, thank you.
If not, let me thank you on behalf of everybody for the very interesting talk that give rise to so many interesting questions. Just to let you know that this was our previous to last, I won't try to pronounce this horrible word, penultimate. It was previous to last IOP lecture. We still have one more coming in April, which will be given by Professor Jonathan Finley, who is the head of the Walter Schottky Institute. He's British himself. He's got a fantastic accent, which now starts to look like German a little bit. He's been in Munich for so much time. He's the big boss of a very big institute, and he will tell us about physics in flatland in 2 dimensions. So please join us for this last talk. Should be an interesting one as well. This being said, thanks for joining us tonight. Have a nice evening, and think or dream about what is the nature of light. Thank you very much, everybody.
Yeah.